The V2U project, which is an autonomous driving by Vanets technology with Sharif, Dan, and Paul.
Good morning, everyone. My name is Paul Smith, and today we'll be presenting our project V2U. Just a brief overview of what we'll be covering. First, we'll have a little introduction to the team. Then we'll go over the motivation, research, and ultimately why we chose our project. Then we'll go on to the design requirements, testing and analysis of our system. And then finally, we'll go over the timeline, cost analysis, and ethical issues we encountered. Like I said before, my name is Paul Smith. I'm a computer engineer here at Manhattan College. My job on V2U is the embedded engineer and also the project manager.
My name is Sharif. I'll be responsible for the computer division of operational network and wireless communication system.
Hello everyone, thank you for coming. My name is Daniel Rossini. I'm an electrical engineering major, and I'm on the hardware team. The big picture for our project is improving road safety and saving drivers' time. On average, New Yorkers spend an hour a day on their commutes, and 90 hours a year sitting in traffic. Furthermore, in 2015 alone, 400 people were injured, and another 3,500 were killed by distracted drivers. Current solutions to these problems include improving public transport, and drive mode on cell phones, and improving collision avoidance technology. But who really wants to sit in a crowded train on their commute every morning? And quite honestly, we don't trust existing solutions to keep drivers off their phones, considering students can't stay off their phones for a 50-minute lecture. Our solution is automation. When it comes to automation, there are 6 levels of autonomous driving. Self-driving cars such as a Tesla are considered to be level 2, self-automation. These systems can accelerate and steer on their own, but the drivers still need to monitor the conditions on the road. New technologies are breaking into levels 3 and 4, which is conditional automation and high automation. Here the car has more control over the operations of the car and more responsibility in sensing the environment, but still there's a driver aspect to the autonomous driving. We want to design a level 5 system, full automation, where all you have to do is sit in the car and say where you want to go. The car wouldn't even need a steering wheel.
So while brainstorming our issues that we have for the project, we decided to make a HP matrix to decide which attributes exactly we be the most efficient. So we decided that our project should be accurate, efficient, and have a reliable communication system. That's why we chose the V2V communication system. So what is actually Vanets? Vanets is short for Vehicular Ad Hoc Networks. It is using the mobile ad hoc networks to the domain of the vehicles. Right now, the new technique for Vanets is using visible light, but since it's so expensive and it's not that common, we're going to use Wi-Fi for our product.
What we are proposing is a revolutionary approach to autonomous navigation. With V2U, your vehicle will be able to see around corners by getting sensor information and traffic information from other vehicles on the network. Not only will this make driving safer for the drivers, but it will also make the road safer for pedestrians as well. Not only will V2U make your drive more safe, but it will make it more enjoyable as well. With V2U at the helm, you will now have your hands free to catch up on that book that you've been meaning to read, or study for that EECE test that's in there. So for our project, we'll be designing 2 prototype vehicles to test and demonstrate our V2V network, or V2U network. These prototype vehicles will be using a few different sensors. One of the sensors it'll be using is an ultrasonic sensor for object detection and avoidance. Another sensor that it'll be using is an IR sensor for lane detection and navigation. We'll also be using Wi-Fi for our V2V network, and this V2V network is going to need a time delay of no more than 100 milliseconds. It will also need to be completely self-reliant as per the ISO standards. Now, most smart cars rely on computer vision. And with our project, we decided not to use computer vision. We did this for a couple reasons. The first reason is that computer vision is very resource intensive. So we would need to utilize much more expensive equipment to get accurate results from computer vision without a time delay. The other reason why we chose not to use computer vision is that we wanted to use a variety of different sensors to accurately simulate a real smart car, which relies on multitude of sensors for navigation and safety.
So this is making sure that parking requirement and security requirement regulation. As shown, we decided that safety and scalability are the most important aspects of our project. And this is our objective tree. So our product is to design a communication between cars, so we can travel time and managing traffic and car accidents. So mainly our product is motivated by the ITS, which is Intelligent Transportation System. Our four attributes for the objective being safety, accuracy, durability, and efficiency. So the product should be safe for all passengers, accurate, takes the right decisions, and durable work under any road conditions and also under any weather condition. Efficiency, the system must be able to send the right orders for the motors and get the right information from the system. This is like a high-level description of our system. We have V2B communication, and we also might have V2I communication, which is vehicle to infrastructure communication.
For the ultrasonic sensors that we're using, distance is calculated by the formula of distance is equal to speed of sound times time divided by 2, where speed of sound is approximately 340 meters per second. The reason for division by 2 is the ultrasonic signal has to travel to the object and back. The infrared sensors that are being used have two working components, an LED emitter and a photodiode collector. The LED will emit a light signal, which will reflect off an object and be collected by the photodiode. This can be used for either distance calculations like the ultrasonic sensor was, or for line detection. For our purposes, we're interested in line detection. So in order to achieve line detection with an infrared sensor, you focus on the light intensity that's being collected by the photodiode. If there's hardly any to no light being collected at all, you can assume that the infrared sensor is over a black surface, because black surfaces absorb light. If there is light being collected by the photodiode, you can assume that's a reflected surface. The navigation in our system is going to be controlled by object detection, lane detection, and communication from surrounding vehicles. These three factors will be inputted into a CPU, which will then output a direction for the car to go, as well as a signal so cars around you know your direction and your projected path. All the components of our system will be powered by a 3.7 volt lithium ion battery. We chose a 3.7 volt lithium ion battery because of its cost efficiency, its size efficiency, and its rechargeability feature. The three inputs into our system are an ultrasonic sensor, infrared sensor, and a receiver. The ultrasonic sensor and infrared sensor are fairly straightforward. If the ultrasonic sensor senses an object within a set threshold distance, the car will stop. If the infrared sensor senses that you're no longer following a line, it's going to adjust course for the motors. The receiver is a little bit more complicated. First, it has to be determined if the signal is coming from a car in front of you or not. If that signal is coming from a car in front of you, that car's signal can directly operate your own motors. All directional outputs will be outputted to your motor driver so you control your own car, as well as a transmitter so you can potentially control vehicles that are behind you.
Now pictured here is our prototype vehicle, one of our prototype vehicles. It's pretty much in its final state. The only thing that's missing in this picture is the left and right ultrasonic sensors, which are required for 180 degrees of object detection. But I believe that's been added at the time of this presentation. Now, since our goal with our prototype vehicles is to simulate real smart cars, we're going to need a GPS system. The problem is that GPS is only accurate within 10 meters, and due to the size of our prototype vehicles and the scale of our track, that accuracy is not adequate. So for our project, we'll be using RFID technology to create a positioning system. Our prototype vehicle will be fitted with an RFID scanner, and RFID chips will be integrated into the track to act as waypoints, which will give positioning data to our vehicles.
So for our software part, since we're using Raspberry Pi as our microprocessor, so we're going to use Python as our coding language. Python is the best for me, the programming language, because it has built-in libraries that makes our life much easier. Like for the infrared sensor, for the ultrasonic sensors, for the motor drive, it has all built-in. Like for example, if you're using any other microprocessor for the ultrasonic sensor, you're going to have to send the sine wave and the receiver receive the sine wave and calculates the time delay and measure the distance. For Python, you only need one line of code to do that. And for our network, we're using Vanets, as I will show in the next slide on a flow chart for the network system. So once the car reads the RFID tags, they have it knows the location now. If the zone is 0, let's say now we're using two cars. If the zone is 0, the car will go to the listening mode, so it's waiting to receive any information from the other car. If it's at zone 1, the car will broadcast a request message and switches to listening mode. So now it's waiting for also another information from the other cars. If car number 1 detects any obstacles, it will send warnings for the other cars. But now it's more like a queue. The first car will take responsibilities for the other cars. Once it's not the first now, the next car will take responsibility for the next one. And this is an iteration video I will film at the first. We had this problem because our sensor will not look right, and as you can see, it's not following at all. And plus, we were using cardboard as our chassis, and it was not holding any of the ports right. So, what problems did we have? At first, we were using computer vision as our link detection and object detection. The problem with computer vision is the program was running all good and it was detecting the object and it being delayed. But the problem is the Raspberry Pi is running 1 frame per second, so it's not actually real time. So, and also in the existing self-driving cars, the car doesn't only use its computer vision, it also uses different types of sensors. So we decided to go with the other sensors. The other problem that we had is the sensor location. At first we had the IR sensors so close to the wheels, so the car would take decisions so fast, so the wheels would go off track right after. And the other problem, as we mentioned before, as was shown in the previous video, was the chassis design. At first we had a cardboard, it was not able to hold the wheels at all. Plus, now we're using a reinforced plastic. And for our final project, we're going to use a 3D printed, we're going to design and print a 3D design for our project.
So our 40% mark was to assemble a working prototype that can navigate a track with line detection. We have achieved this 40% mark, as well as we're now trying to synchronize object detection into this prototype. Here's a video of our working prototype navigating a small loop. And this is at approximately 40% of the maximum speed that the car can go. Our timeline, moving forward, over winter break, we're going to work towards finalizing our prototype and potentially designing our 3D chassis for the car, or 3D printed chassis for the car, as well as working to build our network. Next semester, we plan to simulate our real-life working scenarios to test our car in, such as taking an alternate route if there's an obstacle in your track, or parking, or stopping at a traffic light. The most expensive component when building our project was the Raspberry Pi board at $37. The rest of the components were reasonably priced and usually came in bulk, which helped save our cost. The cost to build 2 vehicles, which is the minimum amount to test the V2V network, is $137. Ideally, we would like to build multiple vehicles to get a more real-life situation. The cost to build a 3rd vehicle is $69, and a 4th would be $53. If there's no unforeseen costs that arise, we would ideally like to build 4 vehicles, and we would be slightly over a $250 budget.
The purpose of V2U is to make your driving experience a more enjoyable one, and most importantly, make the road safer for everyone involved. We believe we can create and revolutionize the optimal driving experience through the use of object detection, autonomous driving, and a decentralized network. Moving forward, we plan to continue to optimize our navigation and object detection systems, implement our positioning system, as well as finalize our network architecture. Now, while working on this project, we had a few standards that we referred to. For the safety standards, we referred to ISO 39001, which deals with traffic safety and management, and especially pertains to autonomous vehicles. For our technical standards, we referred to IEEE 802.11, which deals with the use of Wi-Fi. And then we also are dealing with RFC 793 and RFC 791, which deal with the TCP/IP protocols. Now, going forward, we will continue to abide by NSPE ethics codes, IEEE ethics codes, and as well as follow all traffic and safety laws when designing our project. Now, since our project is designed to take the control out of the driver, we must make sure to take utmost care at every step to protect the users from injury. That's our project. Any questions?